Okay, so what did we learn in the previous class? An important thing that we learned was that some problems which are based on data structures and algorithms, and let's say they are categorized as problems of arrays and maths, they exhibit certain patterns. And the solution is all about deciphering those patterns. Okay, so we'll continue that journey. Okay, and we'll add one more question to that. So let's just begin. Okay, so the question says that you will be given an integer, let's call it n. Okay, so you will be given an integer n, and now it is guaranteed that n is positive. You can take it for granted. Okay, that your number will be positive. Okay, now the question is, what you have to do is you have to count total number of digits that are 1. You have to count total number of digits that are 1 in all the natural numbers, belonging to the range 1 to n. So what is the first step of problem solving? Just read the statement, try to understand what it is saying, and then you can just type in yes. So I'll just glance through it once. Okay, so you have been given an integer n, which is a positive integer. Okay, and now what you have to do is you have to count total number of digits. So you all understand what digits are, right? So if let's say you have a positive number like 9397, so this is an integer, and now this is a digit, this is also a digit. So what are the different values that a digit can have? 0 to 9, right? A digit can be 0 as well, right? I can comfortably have 0 over here, correct? So you have to tell me that if you consider all the natural numbers from 1 to n, where n is a given value, then how many digits are having 1 in them? That is what you have to find. So you can take a dummy input. Let's say you have n equals to 13. Then it means that you have to consider all the natural numbers from 1 to 13, and then you have to count how many digits have value 1 in them. Let's take a look. The natural numbers from 1 to 13 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13, right? These are my natural numbers from 1 to 13. Now just check, now you only check that how many digits are having 1 in them. So if you take a careful look, you'll see that, hey, I have got a 1 here, this doesn't have a 1, this doesn't have a 1, here I have got a 1, here I have got a 1, and again another 1, and then again I have a 1 here and a 1 here. 1, 2, 4, 5, 6. So 6 is the right answer. So how do I solve this problem? Let's begin from the most basic or brute force approach. Okay, so how would the brute force approach look like? You will loop from 1 to n, right? So when you loop over from 1 to n, then you touch all the natural numbers that you have to consider, right? And now let's say you have picked up any natural number. So let's say your n was equals to a value like this. Okay, in that case you would have iterated from 1 to this value, and somewhere in this journey you would have found a number like, let's say 11019, let's say something like this, right? You would have found this number, and now your responsibility is to just check that how many digits in this are 1. Okay, so that can be done by repeated division. So what do you do is, whatever number you have, let's say you have 11019, you can take a remainder with 10. So whenever you take a remainder of the number with 10, let's say you have taken a remainder with 10, mod 10, then you will get the last digit, right? And you can check if this last digit is 1 or not. Okay, if this last digit is 1, then maybe you can increment a count which is initially 0, correct? Otherwise you won't. And then you will change this number. Then you will change this number by dividing it by 10. So when you divide a number by 10, the last digit goes away. So you have 1101, right? And then again, you can take a mod of this with 10, When you take a mod with 10, again you will get the last digit, and then again you will divide by 10, and then the same thing again. You will keep on doing this thing. So as long as this number doesn't become 0, in every step you are taking mod of this number with 10 to figure out what is the last digit, and based on what the last digit is, you increment the count, and also you change this number, you kick off this digit by dividing this number by 10. So this is a process of repeated division and repeated remainder finding, through which you can check that how many digits are 1 in a particular number num. Okay, can anyone comment on the time complexity of just this much part? So you have this number n, let's call this random number as num. What is the time complexity of this part? To just check that how many digits have 1 in them. Order n doesn't seem right, because think of it in this way, how many iterations will be there? Think of it in this manner. How many iterations do you do? See, in every step, one digit is being kicked out, then again one digit is being kicked out. See, in this step this digit was kicked out, in this step this digit was kicked out. So I can say that the number of iterations should be equal to order of digits count. So as many digits are there, those many iterations would be there. Does that make sense to everyone? That your number of operations is totally related to the number of digits that are out there. And now tell me one thing, another way of looking at it is that you have been given a number num and you are continuously dividing it by 10. Okay, so if you keep on continuously dividing it by 10, then after how many iterations that number would become 0? Can somebody talk about that? Can I say that will be log of num base 10? So guys, if you once go through the time complexity chapter, which is already there on your dashboard, you will gain more clarity on that. Anyways, you can just say that yeah, the number of digits that you will have in an integer, even if that integer is a long integer, it would not be more than 18 to 20, right? So total number of operations that you would be doing, let's approximate it to 20 by having this assumption that number of digits will never be greater than 20. Okay, so if you approximate that, then you can say that, hey, every number num that you choose will incur you 20 operations. And how many numbers you are touching? You are touching numbers from 1 to n, so it would have a complexity of almost 20 into n, something like that. And you can just ignore this 20 because 20 is very insignificant in terms of in front of n, so you can say it is order n. But let's say your n is huge. If your n is something like 10 raised to power 18, then this approach is going to time out, right? Because your computer won't be able to do those many iterations, and even if it does, then your coding just will say that, hey, you timed out, I expected a better solution from you. Okay, cool. So guys, I would say that, hey, sometimes whatever the question says, if you start doing that, see, question is directly saying that, hey, whoever reads this question, he would be under the impression that, okay, no matter what, I have to run my loop from 1 to n and then I have to do something. Okay, so if you take this as something that you have to do for sure, then you cannot solve the problem with the right time complexity, right? But sometimes if you do reverse of what question is saying, and when I say the word reverse, I mean something very serious, okay, and I'll talk about that. When you do reverse of something that the question maybe is not saying, then you might be able to solve it quickly, okay? And let's understand that particular point. So guys, think of it in this manner. Instead of picking all the numbers from 1 to n, what I'll do is, I will pick all the place values. I will pick all the place values one by one, and I'll check that how many ones are there at a particular place value, right? So what are place values? Quite a simple thing. If you have something like 1, 7, 6, 9, let's say, this is your place value ones, this is your place value tens, this is your place value hundreds, this is your place value thousands, right? So guys, what I am asking you guys to do is, let's erase them. I would say, first figure out how many ones are there, how many digit ones are there at one's place value. So can you tell me how many digit ones are there at one's place value in the numbers from 1 to 13? and find them out. Yeah, 2 is the right answer because you can see this is place value ones and I have got a 1 over here. This is also a place value ones and I have got a 1 over here. So contribution of one's place value is 2. Now let's figure out the contribution of next higher place value. What is next higher place value? Tens. Okay. So look at the tens place value. So see, tens place value will be present only from number 10 till ahead. So how many digit are 1 at tens place value? So I can see that, hey, this is tens place value and it is 1. This is tens place value, it is 1. This is tens place value, it is 1. So it is equals to 3 over here, right? And apart from that, this is also a tens place value, which is 1. So it's not just 3, it's 4. So I would say that, hey, my overall answer can be written as contribution of different place values. So if I figure out the contribution of place value ones, contribution of place value tens, contribution of place value hundreds, thousands, so on and on and on, and sum them up, then that will also be equal to my answer. So see, when you considered one's place value, then you encountered 11. When you considered tens place value, then again you encountered 11, but this encounter is not a duplicate encounter. Why? Because 11 has got 2 digits, both of which are 1. So it's not a duplicate encounter, it's a fair encounter. So now let's take an example and see what kind of beautiful pattern will come into picture over here. Let's take any random number that you want. Let's take something like n equals to maybe 5149. Okay. So I want to consider all the natural numbers from 1 to 5149 and I want to check that how many digits are 1 in that. Okay. As I said, first I'll find the contribution of one's place value. Okay. So let us find the contribution of one's place value. Can you tell me the smallest number whose one's place value is 1? I repeat the question. Can you tell me the smallest number whose one's place value is 1? Yeah, what is that? That is 1 itself, right? 1 comes. Okay, next higher. What is the next higher number whose one's place value is 1? 11. Next higher, whose one's place value is 1? Yeah, 21. And can you keep saying next? 21, then 31, then 41, then 51, so on and on and on and on, right? Yes or no? Good. So you'll have 21, you'll have 31, and so on and on. What will be the last one? The last one whose one's place value is 1, and that should be smaller than this because I just want to consider the numbers till this point. Excellent. That will be 5141. Rahul, that will not be 91, that will be 5141, right? 5141 is something which is smaller than this and has one's place value as this. Okay? Does that sound good to all? Yes or no? Okay, now guys, if you take a look over here, writing this was very easy because see, you fixed this thing to be 1, right? And now you know that, hey, the smallest number that has 1 in its ones position will be 1, and then it's like you then added 1 before it and got 11, then you added 2 before it and got 21, you added 3 before it, got 31. Similarly, you added 514 before it and got 5141. After this, you would have wanted to get 515. You would have wanted to add 515 because that is which comes after 514. But this thing happens to be greater than this, so this is not worth consideration. Okay, that's the reason this kind of series has been gotten. Okay, so I hope this should make sense to everyone. Is this contribution of ones making sense to all? Yes or no? Okay, cool. Let's talk about tens. We'll make such kind of table for tens. So if you are considering tens place value, what is the smallest number that has 1 at its tens place value? Great, it will just be 10. Because that's a very simple question to answer. Somebody asks you that, hey, the smallest number that has 1 at its tens place value, because I am consciously saying smallest number, so you'd want to keep everything else as 0 and you'd want nothing else to come before it, then only it will be smallest, right? Can you tell me the next few numbers after 10 which also has 1 at its tens place value? 11, 12, 13, and you have many more, right? So you have 11, 12, 13, till what point? Till 19, yes or no? Till 19. Can you tell me the next number which is greater than 19 and has 1 at its tens place value? 110 is the right answer. Good. Yeah. So you have 110 and then 111, 112, 113, so on till 119. What will be the next one which has a 1 there? So it will be 210, then 211, 212, 213, and so on and on till 219. Okay, this will go on and on. So you can imagine this as a family, this as a family, this as a family. What will be the last one that has 1 at its tens place value? I think it will be 5, 1, 1, 0, right? And then after that you will have 5, 1, 1, 1, 5, 1, 1, 2, so on and on and on, and the final one will be 5, 1, 1, 9. Okay, so again, what do you see? See, this 10 is fixed, and initially there was a 0 here, and now you added a 1 before, you added a 2 before, then you would have added a 3 before, 310 family would have come, then 410 family would have come, and finally you have added 51 before. After that you would have wanted to add 52, but this again is beyond this, so this is useless. Okay, so this is about the tens family. Okay, now I would want you guys to just open up your notebook and see if you are able to see a family for hundreds. For hundreds, are you able to observe any such kind of pattern? What will be the smallest number, by the way? Smallest number that has 1 at its hundreds position, it will be 100, right? And then it will not just be 100, it will be 100, 101, 102, so on till 199, right? Right? Okay, so let's list them down. So you will have 100, you will have 101, 102, so on till 199. Okay, after 199 you will get 200, so then you do not have 1 at that hundreds place value. Can you tell me what will be the next number higher than 199 and having a 1 at that position? It will be 1100. Is that clear? Right? So it will be 1100, and after that you will have 1101, 1102, and it will go on till 1199. You can see that this is 111 everywhere. Here also you can see this is 111 everywhere, right? What will be the next one? Next member in this family? Yeah. So you would have 2100, 2102, 2101 basically, and then 2102, and so on and on, 2199. Again you can see 1111. Okay, what will be the final family over here that has 1 at its hundreds position? What will it start with? So it will start with 5, right? It will be 5100, then 5101, 5102, and it will go on till 5199. Guys, I think this is a very interesting pattern. So look at this as a whole, then look at this as a whole, and then look at this entire thing as a whole. You will definitely observe one thing. So see, what is if I call this as a chunk size, this is chunk size for ones, this is chunk size for tens, this is chunk size for hundreds. Okay, so let's say you talk about 100. Can I say, hey, every chunk size is 100? This chunk size is also 100, this is also 100, this is also 100, this is also 100. Yes or no? And what is the gap between any two chunks? If you talk about this chunk and this chunk, how much is the gap between them? 1000, right? Yes or no? See, the gap between this 100 and this thing is of 1000 units, right? So this chunk and this chunk are separated by 1000 units. This chunk and this chunk are separated by 1000 units. This chunk and this chunk. So separation. So this I am going to call as chunk size. So here I am talking specifically about hundreds position. Chunk size was 100 and I can call this separation as time period. Okay. Or let's call that separation only. So if I call that separation, then that separation is 1000. Let's do it here in this tens. In tens, what is the chunk size? Just look at any chunk, 10 to 19, 110 to 119. How many elements are there? Chunk size is 10. And how much is the separation? Just look, 10, 110, 110 to 110. The gap is of 100 units. Now come here. What is chunk size? Any chunk is of size 1. And what is separation? Gap between any two chunks, how much? 10. 1, 10. Okay, 10, 100, 100, 1000. If you consider ith place value, what is the chunk size? The chunk size will be I. And what will be the separation? The separation will be how much? The separation will be equal to 10 multiplied by I. And that is applicable everywhere. So in the ith place value, your chunk size is I and your separation is 10 into I. Does that sound good to everyone? Yes or no? Right? Now this property will help you immensely. This will help you to directly count that how many elements from 1 to n will have 1 at this particular place value. Similarly, how many elements from 1 to n will have a 1 at hundreds place value. It will help you directly count that number. Okay? Guys, tell me, how many chunks will be there? Can you just tell me that? If your number is n, okay, your number is n and you are talking about number of chunks that belongs to this. So how many such chunks will be there? Will it be n upon 10 or will it be n upon 10 plus 1? Let's just talk about 10's place value. How many chunks do you see? 52 is right, isn't it? Yeah. Why is it 52? I'll tell you that. See, when you talk about this tens, okay, first you have a 10 which is kind of prepended with 0. Then it is prepended with 1. Then it is prepended with 2. And then it is prepended with 51. So you started prepending with 0, then 1, then 2, then 3 till 51. So how many elements are there from 0 to 51? So number of elements from 0 to 51 will be 52. Is that clear? Right? So that's an important point to understand. So guys, you can generalize it in this manner that if you are concerned about ith place value, then the number of chunks will simply be equals to n upon I plus 1. 51 upon, so if you do something like 51 upon 5149 upon, basically it will be 10 into I. Why 10 into I? Because separation is 10 into I. That is what I have written. Correct? So if you are looking at 10's place value, then your separation is 10 into 10. So if you do n upon 10 into 10 and add 1 to it, then that will tell you that, hey, these many chunks are there. Okay. Does that make sense to everyone? Okay, cool. Now, there is one thing that we have to be a bit careful about. See, can I say that every number of every chunk will be smaller than or equals to n? I repeat, every number of every chunk will be smaller than equals to n. Is it fair to say yes or no? Just take a sharp look and then say yes or no. I would recommend taking a look over here. You have something like 5199. Before this, 5198, 5197. Are they smaller than equals to 5149 or greater than that? They are all greater than that. So such kind of problem can happen with the final chunk of every family. If I call every place value as a family, then in the final chunk of that, it can happen that first few numbers are belonging to the chunk. So if you talk about this, from 5100, so on and on till 5149, it will belong to the family, but after it whatever comes will not be belonging to the family. So you will have to cancel off their contribution, and it could have happened with the last chunk of other place values as well. So this is to be kept in mind. Does that make sense to everyone, guys? Yes or no? Okay, so that's the only thing which is to be kept in mind. I think I haven't taken the final chunk here. So the final family over here, the final family will be the family of thousands place value. So if you talk about thousands place value, let's do that quickly. In thousands place value, what will be the smallest number that has a 1 at its thousands place value? Smallest number having a 1 at its thousands place value will be 1000 only, right? And after this you will end up getting 1001, 1002, so on and on till 1999. What will be the next number that has a 1 at its 1000 place value? It will be 11,000. But is that number worth being considered? The answer is no, because that 11,000 would be greater than my n. So that is not worth being considered. Okay, cool. So guys, now that we have understood this particular thing, that such kind of relationship exists, okay, and we have also understood some corner cases like these, we should be able to solve it. You know, let's consider a number like 5115. So when you have 5115, don't you feel that some members of this chunk might also be members that I have to eliminate? Yes or no? Yeah, the answer is yes, because everything from 5110 till 5115 is within my range, which is smaller than equals to n, but everything that comes after it is, you know, kind of useless to me. So I'll have to get rid of them. You know, sometimes what can happen? Sometimes even worse thing can happen with respect to the last chunk. See, everything that comes before the last chunk is okay to me. I'm perfectly fine with that. Okay, but just the last chunk can be a bit problematic. So let's talk about a number like 5107. So if your number was 5107, then nothing of this last chunk would have been applicable. Yes or no? Because the first member itself of this chunk is 5110, and this 5107 is even smaller than that. Does that make sense? Yes or no? Right? So that is one thing which you guys have to keep in your mind. Okay. Now, how to solve this problem? So, as I said, instead of iterating on the numbers from 1 to n, you would iterate on place values. So you would begin with place values ones, then you would come to place value tens, and so on and on. So let's say you are considering place value tens. Okay. Then you know that how many full chunks will be there. Number of full chunks will be n upon 10 into I. See, I had written that it will be n upon 10 into I plus 1, but this was a problematic one. The final one was a problematic one. So I would say that n upon 10 into I, this will be the quantity of full chunks. And in every chunk, there are I elements. So this thing multiplied with I will tell me how many elements are there in this. And then for the last chunk, I can take care of it, but I'll take care of that in a different way. Okay, so is this point clear to everyone, that when I iterate my I from ones to higher place value, then for every I, this is the total number of full chunks, and in every chunk there are I elements, so this into I will give me the contribution of them. Okay, now I will give you guys, just take it up as a small challenge. Can you take care of the last chunk somehow? It's not tough to think, by the way. Okay, so guys, think of it in this way. Although I'll be writing the complete code, but before that, it's good to get some fair idea of it. Okay, so let's say if I'm able to figure out that what is the first element and the last element of this problematic chunk. In fact, of all the final chunks. If I'm able to find the first element and the last element, then based on what this number is, I will be very easily able to detect that how many elements from this family qualify to be. Yes or no? Right? You can take a very easy example. So let's say you are able to detect that first is this 5110 and last is this. Okay. Now, if you have something like 5107, then you can check that, hey, this number is smaller than the first. If it is smaller than the first, then the contribution of last chunk will be 0, right? And if you have something like, let's say 5117, which is in between this and this, then the total number of contribution will be this minus this plus 1, because those many elements would be there in between. Now sometimes what can happen is, sometimes you might have, let's say 5127. Okay, so if you have 5127, then that is greater than this. Okay, in that case, everything from here to here would be giving their contribution. So I repeat these cases again. If you are able to figure out the first and the last, then there can be three kind of cases. The number n is something like this, which is smaller than the first itself. If it is smaller than the first itself, then there will be 0 contribution of the chunk. And if it is something like this, which lies in between this to this, then the contribution will be from 5110 till that point. Okay? And if let's say that is even greater than this, then all these things will be contributing. And how many things are there? There are I things. If you talk about ith place value, the size of the chunk is I. Okay, you know, the only thing that you have to play wisely over here would be something like this. You'll have to somehow frame the first element of any chunk. And you know, doing that is not a tough thing. Why that is not a tough thing? Let me tell you that. So if your number n has been given to you, and let's say you are talking about the first element of the last chunk of hundreds place value. Okay, then how you can do that? So you can do that in this way. You can say that, hey, what is actually happening is that the last 3 digits of it will be 100. So all that I have to know is that what is present over here. Okay, and for that what I'll do is I'll do n upon 10 into I. So if I do n upon 10 into I, let's say you are doing 5115 upon 1000. If you do 5115 upon 1000, then what will you get? You will get 5. Okay, and then you can multiply that 5 with 1000 again. So you can multiply this thing with 1000 again. So see, this thing divided by 10 into 100. So this divided by 1000 gave you 5, and then you multiplied that 5 by 1000 again. So it's like getting 5000. And then you can very easily add to this I. So when you add to this I, you will get 5100. Okay, so I repeat this entire thing again. My intention is that I want to know the first element of this last chunk. So for that, I want something like 5 followed by all zeros. Now how do I get that 5 followed by all zeros? If I divide this number n by 10 into I, then I get 5, and then if I multiply that 5 by 1000 again, then it will be 5 followed by 3 zeros, and then I can add this 100, which is I, to it. So this way I'll get the first element. Is it clear how I am able to generate the first element of that last chunk? Right? It's a small deal, guys. You know, you guys can do it on your own as well by using some other technique, but it's not a very big thing to generate the first element of that last chunk. Okay? And now, if you know the first element of the last chunk, what will be the last element? The last element will simply be first plus I minus 1. Okay, in fact you can just take a look over here. So if you have 5100, then the last element is 5199. Why? Because there are 100 elements over here. So the last element will be this plus 100 minus 1. So you know the first element, you know the last element, and then you can have the job done in a very easy manner. Let's do one thing. Let's now quickly implement it all. Okay, so let's say I want to write a function for it. It will be a very small code. I call this as count digit 1. Okay, and it takes a number n and it returns how many digits from 1 to n have 1 in them. Okay, that is what it does. So how do I go ahead? So tell me, what is the first thing that you would want to do over here? What are the different declarations that you want? So one thing that you want for sure is you want to start with a particular place value. You want to start with the smallest place value, that is ones. Okay, so you want to start with long x equal to 1. See, here x is denoting your place value, and every time you will multiply x with 10, then you will be thrown to the next place value. From 1 you will come to 10, from 10 to 100, from 100 to 1000, and so on and on. And then you will have a variable to track called as answer. This answer is the actual answer, which is going to contain that how many digit ones are actually there. Okay, now you will have a condition saying while x is smaller than equals to n. Why I have written this is because let's say if your x, which initially was 1, if it becomes 10,000, then you would just want to stop, right? Because there is no 10,000th place value. The final place value is 1000th place value. Okay, so this is the condition that I have written. Now first let me do the simplest thing. The simplest thing is to find the contribution of full chunks. So how many full chunks are there? The number of full chunks will be n upon 10 into x. This was an extra one, right? So total number of full chunks will be this, and every such full chunk has got x items in it. So this thing multiplied by x can very easily be added to my answer. So that is my first line of code. Does it make sense to all? Right? Okay. Now, what will be the final line of code? The final line of code will be where you will take care of the last chunk. And how do you exactly take care of the last chunk? By figuring out its first element and by figuring out its last element. So how do you figure out first element? So let's say I want to figure out first element. So I'm going to say it again. So let's say you want to figure out the first element. You know for sure that first element everywhere has last two things as 10. Okay, the first element everywhere here has last three things as 100. So you would actually want that you get 51 followed by 2 zeros. If you get 51 followed by 2 zeros, then you can easily add 10 to it and make it equal to 5110. Okay, so what I am saying is that you will divide n by 10 into this particular place value. So that is like doing n upon 10 into x. So see, if you did 5115 upon 10 into 10, so you would have gotten 51. And now you can multiply this thing with 10 into 10 again. So that would have brought 2 zeros to the end. And then you can add a 10 to it. So I get this, which is my 51, and then I multiply to it 10 into x, and then to this thing I'll add x. So this way I am able to generate my first, and then I'll be able to generate my last also, and then I'll be doing my check, and then my job will be done. Last will be first plus x minus 1, because every chunk has got x items, and if first item is being denoted by first, the last one will be first plus x minus 1. Now what you can do is that now see, now you know that hey, if your number is smaller than this, then there is no contribution. So you will talk about contribution if and only if your number n is greater than equals to first. So if number n is greater than equals to first, then there were two cases. So either your number is lying in between from here to here, or it is greater than this, right? So you know you can do that in a single line. You can say that your answer plus equals to min of x comma n minus first plus 1. Okay, so why I have done something like this? See, if my n is greater than equals to this, then there are two cases. First case is that my n is even greater than this. If my n is something like 5121, then I won't say that hey, my answer is the difference of this and this plus 1. Why? Because 5120 and 5121 are out of the range. So I say that hey, my answer will never be greater than x, because this chunk at max contains x items. And if let's say my n is something smaller than this, then this difference will be smaller than x. So then that will be captured. So this single line takes care of that. Does it make sense why I have added min of these things to my answer? Yeah, you do not really need to compute the last. Yeah, I did that just for simplicity. You can just have a first, and through first also you can have your job done. Okay, cool. Now what will be the final step that you will do? You need to jump from one place value to the next higher place value, and your place value indicator is x. So what kind of change will you do to x as the final part of the code? So the final thing will be x into equals to 10. That's it. Yeah. Now take a look. What is the complexity of this code? Everything that you are doing over here is constant operations. There is no loop written over here. There are just few additions, multiplications happening. You can treat it as order 1 only. How many times is this loop running? Yeah, order of log n base 10, because your number x is being multiplied by 10 in every step, right? See, another way to think of it would be, if you have a n as this, then you started off with 1, then you came to 10, then you came to 100, then you came to 1000, then you came to 10,000, and then you were done. So I can say that my number of iterations will be equal to number of digits. Yes or no? Cool. So this is an open source question. It is present on many different platforms. The TOT strategy, which is your reverse lookup. It helps solve many different, and isn't it amazing? So now you are able to say it in just, solve it in just order log n time, log n base 10, and previously you were taking order of n time. There is a drastic improvement. Okay. Yeah. Calling it out again. Why was it a reverse lookup? Because you did not do what the question was saying. Rather, you were doing something else, and doing that something else was, kind of analogous to what the question was asking you to do. Okay, great. So, generally in the problems where you see that if a question is making you to do something, and the process of doing it is like, let's say, doing so many iterations, which might time out, then this sound should come from the back of your head that, okay, let me try something like that once. And most of the times it kind of works. Okay, cool. So now I think we'll do one more question before we are done for the day. So let's say some of the questions you have already seen, right? Find the sum of all the subarrays within an array. Find the sum of all the submatrices within a matrix. So that question itself says that, hey, I'll give you such a kind of dimension that if you even dare to consider all the submatrices, or if you dare to consider all the subarrays, you will time out. Question says that beforehand. So there something should click to your mind. Like here also it was like that. Hey, I'll give you so many numbers that if you start considering them, you will time out, right? So the thing that should come to your head is that, hey, it is not going to be solved like that. Maybe I have to think in terms of contribution, right? So if problem statement and the problem constraints do not agree with each other, so problem constraint says that, hey, I am so huge, you can't do it just like that, then contribution based things come into play. So let's pick the problem. So it's an important interview problem. It has been asked in many different interviews. It's a famous one as well. So yeah, it says that I'll give you a string. Let's call it S. So S is a string which is made up of lowercase alphabets. And I believe lowercase alphabets are from small a to small z. Okay? So it's a string made up of lowercase alphabets. Now, another thing about this string is that all the characters are distinct. Okay? Look at these two things with your hawk eye and tell me, if these two constraints have to apply together, then what can be the maximum size of this string? 26, right? Very good. Because the total number of lowercase alphabets are just from A to Z. Their count is just 26. And because all the characters have to be distinct, so I cannot have A for 2 times or C for 10 times or something like that. So the worst case, by worst case, I mean the longest string that I can have would be a string that has one instance of A, one instance of B, one instance of C, one instance of everything till Z. Okay, cool. So let me pick any such random string. So let's say you have a string which is like F, G, A, B, D, K. Okay. So you have to tell me that what is the rank of this string. And by rank, I specifically mean lexicographic rank. What is the lexicographic rank of this particular string? Okay. So guys, how many of you understand what is lexicography? Alphabetically, right? So the way words appear in dictionary, that is lexicographic order only. So let me tell you one thing. If you have a set of characters, you have D, you have B, and you have A. Okay. What will be the lexicographically smallest string that you can make by using all these characters? Yeah, ABD, correct? ABD is the smallest one. And what will be the largest one? The largest one will be DBA. There will be many others as well, but ABD is the smallest one and DBA is the largest one. Okay. Cool. Can you tell me how many different strings will be there? So the basic question over here is question of permutation, right? Yeah, 3 factorial. Good. And how you are able to say 3 factorial? So if there are n different characters, now the string that you want to make will be of size n. So the number of choices for this is n. And now because one character is used up, so number of choices for this is n minus 1. For this n minus 2, so on till 1. So it will be like n factorial. Here n is 3 and 3 factorial is 6. So ABD is the smallest one. After ABD you would have ADB, then you will have BAD, then you will have BDA, then you will have DAB, and then you will have DBA, right? So I am saying that, hey, this has a rank of 1. So smallest one has a rank of 1. This has a rank of 2. This has a rank of 3. This has a rank of 4. This has a rank of 5. And this has a rank of 6. Is it clear? Are the ranks clear? So the smallest one has a rank of 1 and the largest one has a rank of n factorial. And these ranks are ever increasing. Okay. Cool. So I'll give you a string like this and you will just have to tell me that what is the lexicographic rank of this string among all its permutations. I repeat, if you consider all the permutations of it, what will be the lexicographic rank of this string? This is a problem to be solved. We can take a very small example for your convenience. So let's say your string S is CAB. Can you tell me the lexicographic rank of CAB? So anyway, if we take a look at this example, the different permutations are ABC, ACB, BAC, BCA, CAB, CBA. And I have intentionally written them down in, lexicographic manner. So this rank is 1, this is 2, this is 3, this is 4, this is 5, and this is the one that I have. So the answer over here will be 5. Cool. So yeah, can everyone tell me the brute force solution here? Yeah, generate all strings, right? Yes or no? But tell me one thing, is it a great idea to generate all the strings over here, all the permutations over here? How much time would be spent in doing that, if at all you do that? It'll take you n factorial, isn't it? Yeah, and here your n can be like 26, and if you consider 26 factorial is going to be a huge number, you will definitely time out. So it's not a great idea. Okay, so let's talk about how we can approach it. So see, the first thing that we all agree to over here is that, hey, I can't just do it the conventional way. Okay, so I have to act a bit smart over here. So guys, I can say that whenever it is about lexicographic comparison, there is one very simple statement that can be made. And that statement is, see, this string that starts with S, with F, it will have many different permutations, right? Now, if I ask you to compare two strings, so let's say I have to compare two strings, S1 and S2. So let's say S1 is a string that starts with A and then has something that I do not care. And S2 is a string that starts with K. Can I say that, hey, no matter what is present here and what is present here, S1 will definitely be lexicographically smaller than S2? Can I say that? Because any string that starts with A will come before any string that starts with B or starts with C or D or K, right? So guys, now you all should be able to realize what we want to do over here. So I can say that, hey, out of all the permutation that this string has, there will be some permutations which will be starting with A. There will be some permutations that will be starting with B, some which will be starting with D, some which will be starting with F, some which will be starting with G, and some which will be starting with K, right? So there are certain permutations which will start with A, like you have A, G, F, B, D, K is one of them. Can I say that everything of this family will certainly be smaller than everything in this family? This belongs to this family and everything here will be strictly smaller than this. Can I say that? Yes or no? Right? Okay, great. Once we understand this, then this problem becomes a bit easy. How? Tell me one thing. So consider a string starting with A. Okay. So 1, 2, 3, 4, 5, 6 characters were there. First character is A, then 5 characters remain. Okay. Can you tell me how many members will be there in this family? And then this family? And then this family? 5 factorial, right? Yes or no? Because you have fixed a particular character over here and now you have 5 remaining characters here and 5 remaining choices here. A is gone. So you just want to know how many permutations can be made here by the remaining 5 characters. That will be 5 factorial. So I can say that, hey, there will be 5 factorial different strings in this family, 5 factorial different in this family, 5 factorial different in this family. So I can say that, hey, 3 into 5 factorial. These many strings will definitely be smaller than this string which comes in this family. So definitely if I have a rank initialized to 0, I can add this quantity to my rank. Did everyone understand this idea? Yes or no? Right? And it can be very easily done. How it can be done? You just need to know the kind of status of these characters or rank of characters. Okay, so you can say that, hey, A is the smallest character, then comes B, then comes D, then comes F, then comes G, then comes K. With respect to the characters that are present here, this is the ranking amongst characters. So if let's say I allot some ranks to these characters, so this is, let's say, rank 0, this is 1, this is 2, this is 3, this is 4, this is 5. Then if the rank of this is 3, if the rank of F is 3, that means there will be 3 families of A, B and D coming before it, which will definitely be smaller than it. Okay, and how many pending characters are there in them? 5 pending characters are there. So 5 factorial members will be there in each of them. So I multiplied 5 factorial with this and this is how I got. Now let us focus our attention completely on this family. See, these families are useless, so I'm going to erase them. Okay, now if you focus your attention in this family, how many categories will be there again? So first category will be the one that starts with FA, then the one that starts with FB, then the one that starts with FD, then starting with FG, then the one that starts with FK. You understand what I am saying? So you are fixing the character for the next position one by one and you are saying that, hey, in which family this is going to actually lie. So if you take a look at this, can you tell me in which family will it lie? Starting with FA, starting with FB, FD, FG, FK, in which one will it lie? See, it starts with FG, so it will definitely lie in the family that starts with FG, right? It is going to lie in this family. Now I can say that, hey, all the members of this and this are definitely going to be smaller than the members of this family, right? And now 2 characters are gone, so 4 are remaining in each of them, right? So can you just tell me that how many strings will come over here? 4 factorial. 4 factorial here also, 4 factorial here also, right? So you can say that, hey, you can just multiply that 4 factorial by 3 and again you can add that to your rank. So what is happening? The moment you are selecting your next character, and figuring out which family it belongs to, you are able to consider the contribution of lot of smaller strings, and this is how you go on and on and on. Okay, yeah, it's just like a recursion tree kind of thing, although you don't have to be recursive over here, you can solve it just like that. But is the basic idea clear, guys? Yes or no? How you can approach this problem, right? Yeah. Now you again, do you know that in this particular thing, starting with FG, there can be again different families. There will be a family which will be starting with FGA, then starting with FGB, and so on and on and on, right? So that's how you would basically be proceeding. So now you know that, hey, this FGA, your string belongs to this family only. So there is nothing to be added, right? Because see, if you consider this part, nothing comes before this family. So there is nothing to be added over here. So just think of the logic. You can actually, you can take an example and you can just build logic on top of this. I'm not going to complete this problem. This is like a food for thought for you. Just think, there is just one thing that you have to keep in your mind, and no one has yet talked about that. Tell me one thing. Do I have to update the ranks of these characters or not? After every step, should I update the ranks of these characters? What was the rank of this G? The rank of this G was 4, right? Now basically what you are doing rank of character. This thing is rank of character because rank suggests that there will be few families coming before it. And this is number of characters left. Number of characters left factorial. Correct? So see, G has a rank of 4, but I did not do 4 into 4 factorial, I did 3 into 4 factorial. And why I did that? Because see, this G was coming after F. This G was coming after F. Now, the characters that start with F, okay, their categorization will be FA, FB, FD. It cannot be FF. Why it cannot be FF? Because F is already gone. So whenever a character has been considered already, the rank of all the succeeding character should be decremented by 1 unit. That is one small trick over here. So see, here, how did you do 3 into 5 factorial? You did 3 into 5 factorial because the rank of F was 3. And the strings that start with F will definitely come after the strings that start with A, B, and D. So there are 3 strings, 3 families preceding this F family. So you did 3 into 5 factorial, correct? And this 3 happens to be the rank of F that you had pre-computed. Yes or no? Does everyone agree with that? Right? Okay. Now tell me one thing. Then you come to this step. So basically you move from this character to this character. And now you see that, hey, this character is G. So now when you say this character is G, you know that 2 characters are done and 4 characters are left. So 4 factorial makes sense, but what you would multiply to it should be the rank of G, right? And rank of G was 4. So ideally you should have multiplied 4 with it. Yes or no? Do you follow me here? Because you are multiplying ranks with something factorial. But did you multiply 4? No, you did multiply 3. And why you did that? You did that because this F is already selected as the first character. So in the family following F, you will have FA, you will have FB, you will have FD, you will not have FF. You will not have FF, you will directly have FG. So whenever a particular character is selected, the ranks of everything after it must be decremented by exactly 1 unit. So this is a popular mistake that many people make while implementing this question. So do implement it, and it has a very small time complexity because all that you are effectively doing is you are just iterating on this string and you are updating the ranks after each iteration. And this is just like order 1 calculation, okay? If you pre-compute the factorial of numbers from, let's say, 1 to 26. Okay, sometimes question might say that, hey, your answer might overflow. It might even overflow long. So it will ask you to keep taking mod with M, the kind of question which we did even in the last class. So in that case, just ensure that you are keeping, that you continue taking mods every time, and then you will get the right answer. Okay, bye and good night.